So you can use the voltage divider and the current divider circuits if you have a problem that exactly matches that pattern. But what do you do if you have a circuit that doesn't exactly match? Well, for that we need a more powerful method, and the first such method we're going to introduce is this node voltage method. So what this is about, basically the goal of this method is to find the voltages at all nodes. So hence node voltage method. And we're going to actually do this using Kirchhoff's current law. So using KCL. So we're going to write KCL at each node, which will give us a system of equations that we can solve in order to get the voltages. So let's run through an example and I'll explain how this works. So in order to apply the node voltage method, there's a few steps that we need to follow. And step one is to identify the essential nodes. So an essential node, identify the essential nodes. These are where 3 or more components touch. So in this case here, there's actually 2 essential nodes in this circuit. So we can first of all identify all of the nodes, and we'll check whether those nodes are essential. So for instance, we have a node here, but that's not an essential node because there's only 2 components that touch it. There's the 50 volt source and the 5 ohm resistor. So the essential nodes are this one here and this one here. So these 2 are the essential nodes in our circuit. So having identified those, we're now ready for step 2, which is to choose one of these nodes. Choose one of these nodes as the reference node. And what that means is that all of the voltages will be measured with respect to that node. So we indicate the reference node with a symbol, and we can use the ground symbol, which looks like this, or some people use a little triangle or a triangle that's been colored in. So one of these kind of symbols that we draw onto our node. So usually with a little bit of experience, you can choose which node should be the reference. Often if the circuit layout is nice and neat, it would be the one on the bottom, but it doesn't have to be. You can place it anywhere. It's a good idea to choose a node that has the highest number of branches. So in this case here, we have 1, 2, 3, 4 branches coming from this node. So it's a reasonable choice. We could also have chosen the other node at the top. It also has 1, 2, 3, 4 branches. So actually we're not going to save ourselves any particular work depending on which one we pick, but we'll choose the one on the bottom to be the reference node. So having done that, we then write down, or we give names to the voltages of the other nodes. So in particular, I'm going to write here V1 to be the voltage of node 1. Now, the implication here, basically, where V1 is the voltage of node 1 with respect to the reference. So remember, voltage is always measured between 2 points. So it doesn't make sense to say the voltage of a node unless you mean the voltage of a node with respect to some well understood reference. So it means if I was doing a measurement and I had a little voltmeter and I had connected the red lead of my voltmeter up here onto V1 and I had connected the black lead of my voltmeter onto the reference node, then the thing displayed, the value displayed on that voltmeter is going to be V1. So that's what it means. We're talking about the voltage of this node with respect to the reference that we have defined. So let's tidy that diagram up. So having done that, we're now ready to move on with step 3, which is to write Kirchhoff's current law for all nodes except the reference node. So we don't need to write Kirchhoff's current law at the reference node. We already know the voltage of the reference with respect to the reference, right? It's 0 because it's the same, measured the same thing. Voltage of reference minus voltage of reference is always 0. So we write KCL for all nodes except for that one. And in particular, we usually write this sort of as a sign convention. As a sign convention, draw the currents leaving the node. Now, this is not strictly necessary, but this is convenient for a little shortcut that I will show you in a moment. So we draw the currents leaving that node. So for instance, I have one current here, I will call it I1. I have a current here, I will call it I2, and a current here, I'll call it I3. And then on the fourth branch, I have a current source, and so I don't need to label anything there. That current source is kind of by definition 3 amps, and no additional work is needed. So I can then go and write down Kirchhoff's current law for these currents. So that would be I1 plus I2 plus I3 minus 3 amps is equal to 0. But there's a little shortcut here. And so usually when we do this, we wouldn't actually write down these currents explicitly. We'd kind of skip a step, and I'll show you how that shortcut works. So in particular, let's take a look at the current I1 here, which is the current that leaves our node and flows into the 50 volt source. So looking at that current, I can actually evaluate what that current is using Ohm's law. So in particular, let me write this down. So however, I know by Ohm's law, I1 is the voltage over the resistor divided by the resistance. So the voltage over the resistor, looking at what 2 points are connected to that resistor, they are V1 and the 50 volt source. So the voltage over that resistor is V1 minus 50. All of that is divided by 5 ohms. So this is just Ohm's law. Ohm's law. This is the voltage over that resistor divided by the resistance gives me that current. So this is Ohm's law for I1, and I would do the same thing for I2. So I2 is V1 minus 0, right? It's the voltage over this 10 ohm resistor here is just V1 minus 0, just V1. 0 because of the reference node on the bottom there. They're all working with respect to that being our 0 point, divided by 10. And so you see this is a very systematic pattern, right? So all of this here, systematic pattern, and we can write it directly from the circuit, right? I can write this directly from the circuit diagram, and that's how we would normally approach this type of node voltage analysis. So I would write down these expressions for the current, but do it directly in terms of the voltage. So let me kind of demonstrate how that works. So what I might do, just for reference, because I'm running out of page here, is I'm just going to copy this picture and we'll put it a little bit further down, and we'll go again, and I'll show you kind of the shortcut way of approaching this. So here I am working on step 3 of node voltage method, which is write KCL at each node. Okay, so I have for KCL at node 1, I have the following equation. So I have, looking at the first branch, so just looking at this first branch over here, I have V1 minus 50 divided by 5. All right, looking at the second branch, I have V1 divided by 10, because I see the other end of that 10 ohm resistor is my reference, which is 0 volts in this system that I'm using. The next one is V1 divided by 40, and then the final branch is minus 3. Minus because the current source is entering the node. And I have taken all of my, the order in which I did these subtractions to get these Ohm's law currents was for currents leaving the node. So I just write this down. So with a little bit of practice, you will be able to just look at a circuit diagram and then just write down what will be these equations. And so this is the node voltage method, and we're going to practice developing these equations so that you can kind of just write them down quickly, and then you have the equations, and then it's just a math problem. Right? At this point here, I now have one equation with one unknown, and so step 4 is solve the equations. In this case, I only have one. So let's actually go through and do that. Now, in order to solve this, I would like to get rid of these fractions, kind of multiply by something that will cancel out the fractions. So I'm going to multiply everything by 40. So that will give me 40 times V1 minus 50 over 5 plus V1 over 40 times V1 over 10 plus 40 times V1 over 40 minus 3 times 40 is equal to 0. So this gives me 8 V1 minus 400 plus 4V1 plus V1 minus 120 is equal to 0. Let's clean this up, collect some like terms. So this will give me 13 V1 minus 520 is equal to 0. 13 V1 is equal to 520. V1 is 520 divided by 13. Grab your calculator. 520 divided 13 is 40. So V1 is 40 volts, and that means the voltage with respect to the reference. So previously, when we were drawing voltages on our circuits, right, we would take some node and some other node, and we would write like a plus minus over here, and we would call that, say, V1. So this notation here where we just put a voltage on a node is a little shortcut version of that, and it means always the voltage with respect to the reference. So that's a very important point to understand. We're kind of changing our notation a little bit, just making it a little bit shorter, a little bit easier for us to write. So that's it. That's the node voltage method. So in summary, the process that we followed, we studied our circuit diagram to find the essential nodes where 3 or more components touch. We picked one of those as a reference, and we gave names or numbers to all of the other ones. We then wrote Kirchhoff's current law for each of those nodes. That gives us a system of equations that we can solve, and then we determined the voltages at each of those nodes. So this is called the node voltage method. This is a systematic approach you can use to solve pretty much any circuit diagram, and we're going to practice it quite a bit in this subject, but this is a simple example of applying that method.